Okay, we shall not wait for the rest. Any questions about the previous lesson? No, come. I tell you what, let's quickly revise what we've done last week. So if I give you something like this, very standard kind of diagram. What kind of question is this? Yes, electrolysis. What makes you say so? What is this? Okay, light bulb. There's no external battery, so simple cell. Don't mix it up. I'll just write it cell. And of course, if you see that, make sure you recognize the symbol for the battery. This is electrolysis. Okay, very simple thing. Try not to mix them up. Ethan, tell me, for simple cell, so what is this two thingies called? Or what are they called? Okay, good. And the general name for them is, they are, of course, one is cathode, one is anode, but together they are called, yes. And how about this substance here? It's called, also starts with E. Now, reminder for simple cell, these two electrodes have to be different. So let's say I tell you that this one is the more reactive material compared to the other electrode. Ethan, which is the anode and which is the cathode? This is the more reactive substance. Okay, maybe I be very specific, more reactive electrode. What do you understand by more reactive? More reactive means what, actually? Okay, you may want to write this down somewhere. Now, of course, there are various definitions, but more reactive means that element, for O levels, they normally deal with elements, likes to become ions. So I give you a real example then. Let's say this one is zinc, the other one is copper. Now, if you refer to the table I've given you previously here, of course, they form cations. I think you've written it down somewhere. This one is the most reactive. Notice zinc is there, copper is below. So compare these two, obviously zinc is more reactive compared to copper. Okay? So sooner or later you remember this whole list and more. So let's go back to our question. zinc is more reactive than copper. And they are the two electrodes here. Who is cathode and who is anode?
Copper is cathode.
Good. And obviously the other guy must be anode. Right, so it can be confusing, but try not to be confused. The more reactive metal or electrode becomes the cathode. Becomes the anode. I repeat, the more reactive electrode becomes the anode. Sabrina, at the anode, what reaction is occurring? Oxidation or reduction? Anode. Anode is always oxidation. And of course, cathode is always reduction, always, for all cases, not just simple cell, but for anything else. Okay, let's go a bit more. Dylan, how is my current flowing here? Is it based on my diagram, is it flowing clockwise or anti-clockwise? Current. Now, in case you're not sure, there's one way to look at it. Zinc. Zinc oxidizes, right? I told you it's oxidation. So what does it become? Zinc oxidizes to, there's only one choice. It can only become zinc 2+. And in the process, 2 electrons come out. Where do these electrons go to? Do they go into the electrolyte? These 2 electrons here. Yes, it goes through the wires to copper. That is the flow of the electrons. So electron flow in my diagram is clockwise. Electron flow. Okay, maybe I just write it down. Even though they, okay, once in a while they ask this, electron flow is clockwise. For this diagram. And since all of you study physics here, your current flow, okay, I stands for current, is in the opposite direction. So current will be anti-clockwise. Yeah, there are quite a few things that can possibly confuse you. But of course, you have questions to ask. Actually, there's no such thing as current. Current is simply the flow of electrons in the opposite direction. Okay, next important question, which will almost 100% come up. Which electrode is positive? Which electrode is negative? Now, for me, I look at the current flow for me. Of course, you can remember through other methods. Current, imagine this whole guy is a battery. This whole chunk here, which is true, this whole chunk is a battery. And for a battery, current flows up from the positive terminal. Okay, which makes this guy positive. Okay, current is flowing out of positive, goes through the light bulb is here, goes through the light bulb and flows into the negative. So for me, I normally look at current flow and remember that this whole thing is a battery. For battery, current flows out of the positive terminal, goes through the whatever resistance what you have over there and then goes into the negative terminal. Just a reminder, okay, let your copy now first. What is going to happen to this zinc electrode over time? The battery is not going to last forever. This simple cell is not going to last forever. The zinc will slowly diminish in size. Or okay, I can put it another way, it will slowly dissolve into the electrolyte. Of course, it's going to become smaller and smaller and smaller. And ultimately, when there's no more zinc, then the whole battery doesn't work or the whole cell doesn't work. As for the reason, this is the reason. Okay, your zinc is dissolving into zinc 2 plus. And I repeat, this reaction here is your anodic reaction. Okay, I think I haven't written this word up for you, even though I've mentioned it before. Anodic reaction. Notice it involves electrons. In any anodic or cathodic reaction will involve electrons. And just to help you, in case you are not too sure, whenever you see oxidation, electrons will be on the right-hand side of the equation, always. In case they throw you a equation like this, you see electrons on the right, that is an oxidation. Next question, how about here? What kind of equation? There must be something happening because there must be a reduction happening here. It depends. Depends on what? Depends on the electrolyte. What is inside the electrolyte? Okay, the cathodic reaction depends on electrolytes. Guys, very important question. I did say that this is copper metal, and I did say that it's the cathode, so it's gonna there's reduction here. But important question, so mess this up. Can copper reduce? Can you reduce copper? Think about it. Copper plus, notice there are 2 electrons, right? From this side, I have 2 electrons moving all the way to copper. Can anything happen to copper like that? Think about that. Yes, no? Can copper react with 2 electrons to become what? Answer is no. No. Guys, metals cannot reduce. I don't know whether you have already figured that out. There's no reaction. This reaction will not occur. Okay, metals cannot reduce. At least based on your syllabus. So something else must be reduced. Okay, something else. I'll just give you one possibility. Let's say my electrolyte is HCl. Okay, or more commonly, H2SO4. Okay, this is quite common, especially in car batteries, they use H2SO4. So what's the reaction going to be? In this case, this will happen. Okay, if my electrolyte is H2SO4, then this is your cathodic reaction. And okay, just to spell it out in case you all need to use the word cathodic reaction, it's this one. Now, just now I was asking you, what happened to the zinc? Well, I've already answered, it slowly dissolves into the electrolyte. It's going to become smaller and smaller. Next question. Will you observe at the cathode then? The anode zinc becomes smaller and smaller and smaller. How about the cathode? What would you observe? To answer that, look at your reaction. Look at this cathodic reaction. What would you observe based on this? Sabrina? Based on this reaction, what will you observe? Yes. Okay, you will see your bubbles around the cathode. Okay, those are hydrogen bubbles. Will the copper cathode disappear? Will it become smaller? Answer is no. Nothing's happening to the copper. All right? Can. So the copper electrode or the copper cathode will remain as it is, except that you're going to see bubbles on it. But the cathode will not become smaller. Or of course, neither will it become bigger. Okay, any questions? No? Okay, I'm actually basically just revising last week's stuff. Let me just quickly revise electrolysis as well. Okay. So to identify all the standard things. Now look at the diagram I've drawn. Dylan, which one is anode, which one is cathode? Anode is left or right? Okay, first thing, look at the battery. Negative, positive. Can or fire? Right. And maybe I jump too fast. I'll rephrase my question. Which electrode is positive? Which electrode is negative? Now, for electrolysis, it follows the battery. Negative will force this guy to become negative. Positive will force this guy to become positive. Okay. Okay. Next, where's my current? Clockwise or anti-clockwise? Dylan? Current? Clockwise, anti-clockwise. Okay, now try to follow. This is a battery. And for any battery, the current will flow out of the positive terminal. Goes through the electrolyte back to the negative terminal. So current is clockwise. But for electricity, bear in mind, electrons will always flow in the opposite direction to current. Okay, so electrons will be in the opposite direction. Of course, I still haven't answered my earlier question. Which one is anode? Which one is cathode? Right. Left or right? Anode? Right, good. This is the anode. Now, once you identify this correctly, obviously the other guy must be cathode. How do I know? There are a few ways. One of the ways I remember is, notice electrons are lost. Okay, electrons are lost from this guy. Like electrons are coming out. So therefore, anytime electrons are lost, that constitutes a or an oxidation. And electrons are lost from this guy. And this guy must be undergoing oxidation. And hopefully you still remember redox oxidation means loss of electrons. And once you know it's oxidation, it must be the anode there. And remember, oxidation is always anode. Anode is always oxidation. Now, once you know this, then it's a very simple method to fill in the blanks on the other side. But of course, I can also rationalize by saying, remember my electrons, where are they going? They are going through this battery and straight here. Electrons are going into this guy, no? Which means what? This guy is going to reduce. Reduction is the gain of electrons. This guy is going to gain a lot of electrons. So this guy will undergo reduction. And once you know this guy is reduction, you can deduce that it's the cathode. And just remember this, cathode reduction, anode oxidation. Or vice versa. I mean, oxidation is anode, reduction is cathode. Any questions? No? Okay. No? All fine. But of course, you need some practice. We really do. I think I have gone through 2 situations for the electrolysis. Altogether, there are 6 standard situations based on the notes I've given you. At least one or more of them will come up. In fact, if you look closely, look at the 6 situations I've given you here. If you look closely here, can you group them together? You notice this is sodium chloride, sodium chloride, sodium chloride, copper sulfate, copper sulfate, copper sulfate. So you can loosely group them into 2 groups, sodium chloride versus copper sulfates. So I suspect 2 questions will come up. One on sodium chloride, the other one on copper sulfate, at least 2. But you're likely to have more than that. That means the 3rd or 4th question will come on something new that is not a standard. That is not a standard even the standard given here. Okay. Yes, I think we stop at number 2. Yeah. Okay, look at number 3. Concentrated sodium chloride. Try to follow. So first thing, as always, draw your cell diagram or your circuit diagram. Same thing, 2 electrodes. This is electrolysis, so there must be an external battery. Okay, this is scenario number 3. Now, fill them in with whatever you know. Sodium chloride, but concentrated. What else do you know? What electrodes are being used? I think they use carbon. Yeah, okay, carbon electrodes. But actually, it's not usually not carbon itself, it's graphite. Okay, so never mind, I just write it in carbon electrodes. Just know that carbon electrodes are usually inert. Usually. Okay, come. What else can I write? Electrons? What's the flow of electrons? Coming out of the negative terminal electrons. Of course, current is in the opposite direction. I mean, of course, if you know all of this very well, then obviously no need to write them out. But if not, I strongly suggest you write them out. Come, quick one. Who is cathode? Who is anode? Left is, yes, good. Left is anode. Because positive terminal, electrons are removed. Loss of electrons means anode. Anode means oxidation. The other guy is, of course, cathode, which, of course, always links to reduction. What next? Ask yourself, what's inside electrolyte? What are the cations? Sodium plus. What else? It's aqueous, isn't it? So you should have. Yes, good. Same thing. Write down the anions present. Shouldn't be a problem. Reminder, I mentioned this last week. Yes, I know there are a lot of new concepts. Cations will go to cathode. That's why they are called cations. That's the definition of cations actually. Anions go to anode. Next question. Next question, important question. I have two cations. Ask yourself, which one is discharged? Is it sodium plus or is it H plus? Oh, that's the technical word you need to know. Discharge. Actually, it's a fancy word. Basically, discharge means undergo reaction. Same thing for anions. Ask yourself, which is discharge? Or which is going to undergo reaction? Now, of course, the reaction of interest for anions will be oxidation, whereas for cations it will be reduction as always. As always. Cations go to cathode. Cathode means reduction. Now, let's look at cations. Sodium versus hydrogen. Go to your list. Go to the table. Sodium is right at the top, very reactive. H plus is right at the bottom, less reactive. But be careful here, look at this arrow. Ease of discharge increases downwards. So between these two, who is going to get discharge? This guy. Yes, I did say that this guy is less reactive, but the order of discharge is in the opposite direction. Okay, so this guy is lower, it tends to get discharged. Okay, so go back to my table. I mean, go back to my diagram. In this case, for cation ions, the answer is H plus. So write the equation or write the reaction out. In this case, what happens to H? H plus is at the cathode gain electrons. Electrons on the left-hand side. This is gain of electrons. Nothing new. You see this equation again. H plus is converted to H2. So this is your cathodic reaction. Oh, sorry. Cathodic reaction, the reduction reaction. But anions. Get these two guys. Look at your list. Chloride and hydroxide. Where are they? Oh, this one is tricky. Try to follow. Chloride is here. Hydroxide is there. Ordinarily, who is going to get this charge? If I look at this table. This guy, right? This guy. Ease of the charge increases downwards. So whoever is lower will get this charge more. Can this guy? But the but is important. I did. Write this now, didn't I? This is important. Try to put a highlight or something. This thing. Concentrated. So I have a lot of chloride. So in this case, there's an exception. In this case, I go back to my list. This guy doesn't get discharged because this guy is more concentrated, a lot more concentrated. So this guy gets discharged. Instead, put a asterisk star or whatever somewhere. This is an exception. So whoever gets discharged doesn't just depend on the order here. It also depends on the concentration. Maybe I write it up for you somewhere at the diagram. So in this case, chloride gets discharged because it is concentrated compared to OH minus. I'm not done. What's the equation there? All right. What does it form? Remember, this is N ion. N ions undergo oxidation. Oxidation means electrons on the right. Chloride will form. It will lose electrons to form chlorine gas. Balance it. That is your answer. Okay. So that is scenario number 3. Questions, anyone? Dylan, okay.
That one didn't Na plus get discharged.
Yes, very, very good question. That is the difficult part. Now, I go back to this list again. Na plus and H plus. Well, let's be a bit clearer. I write it down. Na plus is concentrated, right? Didn't I say that?
Yeah.
But something else comes into play. The distance between them is very great. There's a great interval. So the tendency for this guy is still stronger despite the higher concentration. That is the difficult part. It's a huge interval between the two of them. So the tendency for H plus is still greater. despite the more concentrated Na plus. Of course, if you go further up, like A level or polytechnic or university, they actually have equations for calculating this. But for now, that's all you need to know. And right, let's go on. Now draw the diagram for scenario 4 as well. Okay, fill in whatever you need, like who is the cathode, who is the anode. What are the cation ions present? What are the anions present? Of course, if you still have issues with those things, better voice out, let me know. Okay. Of course, you can compare against mine if you need help. Also watch carefully, read carefully. Copper sulfate, did they mention concentrated? No, they didn't say that. So we assume all of them are dilutes. Okay, draw the electron flow, draw the current flow if you want to. Okay, who is going to get discharged? If you need help, compare against what I've written down. Decide who is going to get discharged and what is the reaction. Ethan, done? Still doing. Okay. This one should be quite straightforward. There are no special conditions. Copper 2 plus should be discharged. Hopefully you have identified it correctly. OH minus should be the one discharged. Okay, come Dylan. Copper 2 plus. What reaction will it undergo? Yes, good. Remember, it's a reduction gain of electrons, meaning electrons on the left-hand side. OH minus, hopefully you still remember what happens when you discharge OH minus. Yep, Sabrina, what do you get when you discharge OH minus? You get oxygen. And how about the H? What happens to the H? No, you can't have both oxygen and hydrogen at the same time. You can only have oxygen and water. Okay, so oops, I've written the electrons wrongly. Sorry about that. Okay, balance your equation. You can check against my answer. I'm not done. The question normally will ask you observations. What will you observe at the anode? What about the cathode? Hopefully you notice anode releases oxygen O2. So you will see bubbles or effervescence there. Oxygen bubbles. But how about the cathode? What will you observe? Copper is formed, doesn't it?
Gets bigger.
Yes, possible. Your cathode will get bigger, but what is your cathode made of? Did they put it down? Platinum, right? I think in your diagram they put platinum. So this is a platinum cathode. Yes, possible your, let me use a red color. So your copper can coat around it. It will deposit around it. Copper, obviously the color you have to remember. No, by right. If copper is pure, it's pink actually, if it's pure. But over time, it will turn a brown coloration, which is quite normal. So Dylan is correct. Your cathode may get bigger, may. However, sometimes your question also tells you this, the deposit may get too heavy. If you drop to the bottom of the container. Okay, so sometimes your question will tell you see some sediment at the bottom. That is basically due to the cathodic reaction. Okay, your deposit dropped to the bottom. You see some sediments there. It's possible as well. So be open-minded about it. Copper sediment or copper deposit if you want. I think sediment is more correct. Any questions about this scenario form? Ethan? Okay. Sabrina? No? Now, if that's fine, guys, can you also draw and write down the scenario 5? Go through the same thought process. How to analyze scenario 5. Of course, I still advise you to draw it out. It's much more easier to visualize. Take note of the special condition. Take note of the electrodes. What are the electrodes made of? Oh, Serena done? Never mind. Don't go through everything first because there's a special condition here. Okay, come guys, there's a special condition that you got to be careful of. Now, maybe you've drawn something up to what I've drawn on the screen right now. So the next question is, who is going to get this charge? Right, as always, who is going to get this charge? Now, if you look at the table, copper is going to get this charge. All right. Well, yes, you're correct. Copper get the charge. And remember reduction at cathode. So it's going to gain electrons. It's going to become solid copper. Nothing new, nothing new. But here, be careful of the anode. Who is going to get this charge? There is a slight problem here. The problem is this. Just now, for scenarios 1 to 3, what kind of electrodes are we using? Platinum, carbon. Now, I think we wrote last week. I hope you wrote it down. Okay, we erased it already. Most of the time, platinum and carbon are inert. They are inert electrodes. They do not engage in any reactions. Of course, there can be exceptions, but in general, they don't. They are inert. But copper is not. Copper is still considered active, even though it's not that active, but still counted as active. And therefore, this is a special condition. So let's go back to our diagram. Keep that in mind. Be careful when you see copper. So let's go back to our diagram here. If I analyze the cathode, okay, so if yes, I think we have mentioned this, there's copper 2+, there's 6+, but how about the cathode itself? Cathode itself is copper. Okay, so ask yourself, can copper be reduced? No, I think we answered that just now. Hopefully you remember. So the answer is no. Therefore, don't worry about copper cathode. Copper cannot be reduced. So don't worry about that. But anode is a different story. Okay, it's not okay. I mean I shouldn't have linked it with anions. It's not strictly counted as an anion, but as the electrode itself, you still have to consider that can copper be oxidized? The answer is yes. Right. The answer is yes. So therefore, in this case, copper is the one that gets discharged. So What does it oxidize to? Remember, oxidation means electrons on the right-hand side represents a loss of electrons, so it oxidizes to copper 2+. This is your anodic reaction. So let me write the explanation for you. Due to the active nature copper electrode, it is oxidized in preference to the other anions. So that is the point this is the reaction you may want to highlight. This is an exception due to the special condition of the electrode. Okay, your electrode is copper, so it's active and it can be oxidized, even though it cannot be reduced. Okay, Ken? One last part. Why do we do this? When do you see this kind of application? All right, you better write it down somewhere. It can come up. This is sometimes, for this setup, it is used for the purification of copper. So what happens is this. I have anode being an impure piece of copper. Okay, anode, I put an impure piece of copper there. It could be mixed up with other elements, other substances. And on the cathode, normally I don't use a large piece, I use a small piece, but doesn't matter. I put a pure piece of copper. So if you look carefully, what's happening? This guy is oxidizing. So observation, what happens to this? It will slowly become smaller and smaller and smaller. As the copper dissolves into electrolyte. On the other hand, for the cathode, what is the reaction then? You know, this is the exact reverse. These two reactions are reverse of each other. Hopefully you notice that. Okay, so essentially, this cathode will become bigger and bigger. But the point is this. On the cathode, pure copper is deposited on it. So this is going to become bigger and bigger with pure copper. So if you think about it, what is happening? From the anode my copper 2 plus goes in the solution or electrolyte, it actually migrates to the cathode. And at the cathode, this copper 2 plus goes back to become copper metal. So that is what is happening. There is actually a movement. So from the anode, the impure copper is extracted for the pure copper, which migrates to the cathode. Okay, so whatever impurities here, what happened? Normally they'll drop down. Okay, maybe I just draw it in case your question comes up. I may have some sediments here at the bottom of the anode. These are the impurities. Could be other elements, maybe zinc, aluminum, or something. Okay, questions? Okay, no. Okay, lastly, before you draw scenario 6, I need to make an amendment. Okay, done. Sabrina. Look at scenario 6. I think there's an amendment I need you to make. Can you change this cathode to the object to be plated? Okay, it's not carbon. For scenario 6, cathode is the object to be plated. Example, let's say you want to plate a steel fork. You want to plate it with copper, you can do that. Same thing, guys. Try to draw up scenario 6. Or fork at the cathode. I mean, if you want to use my example of a steel fork or stainless steel fork. I assume you know how to label which one is the anode, which one is the cathode by now, so I won't write those. Now, again, you may want to pause as well, because again, this is a special case. There's a special condition present. Instead of focus on the reactions and the observations. Now, the special condition is this. Anode is copper, which is still counted as active. It's not an inert electrode. Steel, what do you think? Steel is pretty active too. Okay, so these are not inert electrodes, so bear that in mind. So therefore, at the cathode, where the cations are, where reduction takes place, I also have to count in my electrode here. Oh, sorry, electrode is steel in this case, sorry. No, copper, steel. Now, likewise, for the anode, I also have to account for my copper electrode, copper anode. And this one, we have already done it already. Because of this copper electrode, copper gets oxidized instead of the other two anions. Nothing new. This is similar to scenario number 5. But write out the equation. Now, cathode. Cathode is very unusual in the sense that steel is active, but does steel get reduced? Can you reduce steel? No, you can't, but steel likes copper a lot. They are metals. All right. Steel is an active metal. Copper is a relatively active metal. Steel likes copper. So as a result, guess what? Your copper likes to stick to steel. So because of the steel, copper 2 plus, oh, actually no big deal here. Sorry. Actually here is, sorry, actually I don't need you to think about that because it doesn't matter. Because for this case, copper 2 plus still win. Right, it doesn't matter. I don't have to think about the electrode that much. So I can simply say that copper 2 plus get discharged. So copper 2 plus get discharged based on the normal rules. Okay, I think nothing new here. So observation, right now, your anode, what will happen to it? Right, slowly dissolves over time. It becomes smaller, of course. Whereas your steel form, if you design everything properly, it will get plated with a layer of copper. If everything is designed properly. Okay, so when do you do this? I'll practice now. This is likely to come up. Electroplating. This is called electroplating. In this case, I electroplate my steel fork with copper. In this case, but you can do other things too, which may come up for you. Okay, any questions? Now, even though not part of your 6 standard scenarios, let me give you an unusual one, which can happen, or if you can try this at home. Come guys, if you are interested in electroplating, so let's say, again, we have our steel fork. You don't like your stainless steel fork, it looks really ugly. On the other hand, you have a lump of gold. You have a gold coin here. Notice everything else is still the same. You still have your 2 electrodes. You still have your electrolyte. But the important thing is you are trying to plate your fork with gold, which can be done if you have the gold with you. As long as your gold is at the anode, fork is at the cathode. Oh, but reminder, your fork must still be a conductor. Please don't try to plate a plastic fork. It doesn't work. It has to be a conductor, a steel usually, steel fork with gold. But there's one more requirement. What's the last requirement for this to work properly? You need a solution of gold ions. Right, so for O levels, no need to know how to rate that solution. Okay, because gold doesn't dissolve in water well, but there are ways to get around it, which for you, there's no need to know. Okay, okay, so that's how you plate your fork with gold. All right, any questions, anyone? No? Just one last thing. One last thing that may or may not come up, but it's in your syllabus. This one is very special. Hydrogen fuel cell. Some schools like to ask this, but some schools don't bother with it. Some schools can create an entire question with the hydrogen fuel cell, entire question based on this hydrogen fuel cell. It looks like this, but I'll simplify it for you. Come guys, let's draw a simple diagram. Hydrogen fuel cell. So get used to seeing this term. It may come up for your school. So it depends on your school. But it's definitely part of the syllabus. Now, same thing. I still need 2 electrodes. Okay. Okay, I make this use red instead. This is the cathode. The other is anode. But I also want to stress something. The electrolyte is not exactly aqueous or liquid. That is the unusual thing. In real life, electrolyte can be a solid too, but no need to explore too much into this for O levels. So I have something in between. Okay, this is a solid. There's an official name for that, even though you don't need to remember. Just know that it's a solid electrolyte. And it's called, for this case, for this hydrogen fuel cell, there's a name for that, which you depends on your school may or may not ask you about that. Proton exchange membrane. I think for now, no need to remember that. Because if your school comes up with this question, it will give you a whole long story. Okay, but what do you need to know? Okay, you need to know that at the cathode, you have to pump in hydrogen gas. Okay, you have to pump in hydrogen gas. So that is why it acts as a fuel. Some quick ones, Sabrina, cathode oxidation or reduction? Reduction. And cross oxidation. Hold on, did I mix up something? Give me a moment. Oxidation. Oh, sorry, it's the other way around. Hydrogen gas is at the anode. Now, what happens is the H2 gas will oxidize. To what? This is the equation. No surprise. It's going to change into H plus. Okay, can. Just a note. What's H plus? H plus is what is it exactly? It's a hydrogen atom without the electron. So what is left? It's just a proton. You think about it. H plus is a proton, because your electron is gone already. And the thing is, this proton, where does it go to? No surprise. Proton goes into the electrolyte towards the cathode. No surprise there. That's why they call it proton exchange membrane. The proton goes from anode to cathode. But the electrons, where do they go? Can they go into the electrolyte? The answer is still no. So there must be an external circuit. Electrons go into the circuit. Okay, so be very clear about this reaction here. H plus goes across the membrane to the cathode. Electron goes into the circuit, and of course, it is going to light up this bulb. But how about here? Cathode is still reduction. What is going to be reduced? Now, for that, I need something else. I need to pump in O2. Or sometimes air. But it's the O2 that's reacting. Okay, so no surprise there. O2 reacts with what? Remember reduction, right? Electrons will be there, of course. Sorry, not electrons, because remember the electrons go into the cathode, so electrons will be there. But what else is there? Don't forget H plus. Okay, So this is the catalytic reaction or the reduction reaction. What do you get then? No surprise, you get water. Okay. So balance it. Okay, make sure you balance it. And just to finish off everything, what is going to come up here? Right, basically the leftover air plus water vapor. Okay, questions, anyone? Of course, you may ask, how about hydrogen? By right, hydrogen is limiting by right. You do not want hydrogen to actually come out into the atmosphere. Why? You want hydrogen to go into this fuel cell to generate electricity, but you don't want to let your hydrogen to escape. Hydrogen should be limiting. It should be all used up. Why? What is so special about hydrogen, H2? Guys, try to respect hydrogen. It's flammable, explosive. Okay, so it's dangerous to release hydrogen into the surroundings. So make it a limiting reactor. Okay, so yeah, anyway, just to emphasize my point, what is a hydrogen fuel cell? It's not electrolysis. Guys, look carefully. Does it look like electrolysis? No, this is actually a cell, but even though it's not simple cell, it's a hydrogen fuel cell. So essentially, it is a battery. So since it's a battery, come put in which one is positive, which one is negative, which electrode is positive, which one is negative. You should identify correctly. This one is positive. This one is negative. How do I know? For me, I normally look at the current flow. Current flow is opposite to electron flow. Current flows out from the positive terminal of the battery. Current always flow out of the positive terminal, goes through your circuit back into the negative terminal. I mean, for me, that's my way. You may have your own way to remember that. Okay, one last thing which may come up for your school. Now, you notice, look at all these reactions. Electron, 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 electron. All these equations have electrons inside. But what if they ask you this? Go back to the hydrogen fuel cell. The question asks you to write the overall equation. How are you going to write it? It may come up. The trick is this. Look at my catalytic reaction, 4 electrons. Can anodic reaction, 2 electrons. Can I multiply by a multiple of 2? Two times 2, 4. 2 times 2, 4. Okay. So basically, I'm trying to make the number of electrons the same. Then I add the cathodic and anodic reactions together, or equations together. What do you get? I get 4H plus O2 plus 4 electron plus 2H2, and I get 2H2O plus 4H plus 4 electron. This is what I will get. Next, cancel out the same entities on both sides, cancel off the 4 electrons. That's why you must have 4 electrons, 4 electrons. What else can I cancel? 4H plus, 4H plus. So what is left? This is your final answer for the overall equation. So, yeah, try to remember this overall equation concept. It may come out, in fact, high chance of coming out. Okay, any questions, anyone? Of course, if you think clearly, they can ask you about other scenarios too. Let's say for this one, scenario 3. From scenario 3, how to write the overall equation? This one's really quite simple. Electrons are the same on both sides. Okay, scenario 3, you should get something like this. You should get this. So scenario 3, nothing, I think nothing fanciful here. Scenario 3. Reminder, overall equation does not involve electrons. Make sure you don't show any electrons inside. That's the key point. That is the important point. You can try the same for the other scenarios. Likewise, not just for electrolysis, but for simple cell as well, you can do that too. Okay, this was the cell that we did earlier at the beginning of the lesson. What's the overall equation? You know this is an ionic equation. Okay, so basically I combine this equation and this equation here and getting rid of the electrons. You will get this. An ionic equation. Okay, questions, anyone? I still feel that this is the most difficult chapter, personally speaking. So try to grasp as much as you can. Ethan, any questions? Huh? Right, go back and read through. You still need a lot of time to digest. Sabrina? No? Is your school starting on this now? Oh, activity series. Dylan, anything to ask? No one? Okay, then if not, I shall end it here.